Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The cosmos stretches beyond our imagination, a tapestry of billions of galaxies scattered across the expanding universe. Among them, one stands out in our celestial neighborhood, Andromeda, also known scientifically as Messier 31 or M31. At 2.5 million light-years from Earth, it represents our nearest major galactic neighbor, a spiral beauty that mirrors our own Milky Way in many respects, yet harbors its own unique mysteries. Through the lens of modern astronomy, Andromeda reveals itself as a colossal system containing approximately 1 trillion stars, nearly twice the stellar population of our home galaxy. This massive collection of stars, gas, and dust spans 150,000 light-years across, creating a celestial metropolis of overwhelming proportions. Within this vast expanse lies potential we are only beginning to comprehend. The quest to understand Andromeda began long before our modern technological era. Persian astronomer Abdul-Rahman al-Sufi first documented this little cloud in 964 CE, making it one of the earliest recorded observations of a galaxy beyond our own. Yet it wasn't until the early 20th century that Edwin Hubble conclusively proved Andromeda existed outside the Milky Way, forever changing our cosmic perspective. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Today, astronomers study Andromeda with tools Abdul-Rahman could never have imagined. From the Hubble Space Telescope to the James Webb Space Telescope, from radio arrays to gravitational wave detectors, these instruments reveal a galaxy teeming with stellar nurseries, aged globular clusters, and mysterious regions that beckon further exploration. The statistics alone present a compelling case for extraterrestrial intelligence. Conservative estimates suggest Andromeda contains approximately 100 billion planets, with potentially billions residing in their stars' habitable zones, the Goldilocks regions, where conditions might support life as we understand it. Even with extremely low probability assumptions, the numbers suggest thousands, perhaps millions of worlds where complex life could have evolved. But the case for intelligent life in Andromeda extends beyond mere statistics. The galaxy itself is approximately 2.5 billion years older than our Milky Way, providing substantially more time for biological and technological evolution. This head start, measured in billions of years, represents an almost unfathomable evolutionary advantage for any emergent life forms. Beyond age, Andromeda's structure offers intriguing possibilities. Its spiral arms, much like our own, provide stable environments where solar systems can exist relatively undisturbed by cosmic catastrophes for billions of years. Its metallicity, the abundance of elements heavier than hydrogen and helium, appears sufficient for forming rocky planets and the complex chemistry life demands. As we peer across the void separating our galaxies, we must consider a humbling possibility. We may be observing a galactic civilization, or many such civilizations, that achieved technological maturity while our own planet was still forming. The light reaching our telescopes today left Andromeda 2.5 million years ago, when our human ancestors were first developing stone tools. What might have transpired in the intervening millennia? This series explores not just the possibility, but the probability of intelligent life in our neighboring galaxy, examining the scientific evidence, technological signatures we might detect, and the profound implications of making contact with an Andromedan civilization. The journey takes us to the frontiers of astronomy, biology, and our understanding of intelligence itself. Just as stars possess habitable zones where planets might support life, galaxies themselves contain regions more conducive to life's emergence and evolution. The concept of a galactic habitable zone, GHZ, represents one of modern astronomy's most fascinating frontiers, a region within galaxies where conditions optimize the development of complex life forms and potentially technological civilizations. In Andromeda, This zone likely follows a pattern similar to our own galaxy, not too close to the chaotic center, where intense radiation and gravitational forces create inhospitable conditions, and not too far in the sparse outer regions, where star formation may be insufficient to generate enough planets with necessary heavy elements. Instead, the sweet spot exists in the galaxy's middle regions, particularly within its majestic spiral arms. Astronomers estimate Andromeda's GHZ might encompass several 100 billion stars, a staggering number that dwarfs even optimistic estimates for our own galaxy's habitable region. This difference stems partly from Andromeda's greater mass and different stellar distribution, creating a potentially larger zone where life-sustaining planets could orbit stable stars. The panchromatic Hubble-Andromeda Treasury (PAT) survey, completed in 2014, mapped over 100 million individual stars in Andromeda, revealing detailed structures within its spiral arms. These observations show regions remarkably similar to our own local galactic neighborhood, the same type of environment that fostered Earth's biological complexity. Within Andromeda's GHZ, multiple factors converge to create potentially life-friendly conditions. First, appropriate metallicity levels provide the necessary building blocks for rocky planets. Studies indicate Andromeda possesses metallicity gradients similar to or even higher than the Milky Way, suggesting abundant materials for planet formation across its habitable regions. Second, star formation histories in Andromeda's spiral arms reveal patterns of sustained stellar birth without catastrophic disruptions. These patterns have persisted for billions of years, creating the cosmic stability life requires to evolve from simple to complex forms. Within these regions, stars with lifespans sufficient to support biological evolution, particularly K and G-type stars similar to our Sun, exist in abundance. Third, Andromeda displays lower rates of potentially life-destroying events such as gamma-ray bursts compared to more chaotic galaxies. While no galaxy offers perfect safety from cosmic catastrophes, Andromeda's structure and evolution suggest large regions have remained relatively sheltered from extinction-level events. Perhaps most intriguingly, Andromeda contains numerous globular clusters, dense collections of ancient stars that have orbited the galaxy for nearly its entire existence. These clusters, some containing stars nearly 13 billion years old, could represent some of the universe's oldest continuously stable environments. Could advanced civilizations have emerged in these ancient stellar communities, evolving over timescales that make human history seem insignificant by comparison? Recent observations from the JWST have identified several promising regions within Andromeda's habitable zone. One area, designated M31HZ alpha, contains an estimated 17 billion stars with characteristics similar to our Sun, all within a region where supernova rates appear low enough to permit long-term biological evolution. These discoveries lead to profound questions about the potential diversity of life in Andromeda. With billions of potential life-supporting star systems spread across regions with varying galactic conditions, the possibilities for different evolutionary pathways multiply exponentially. If life exists in Andromeda, it likely represents not a single civilization, but potentially thousands or millions of different biological and technological experiments playing out across the galaxy. The implications extend beyond mere numbers. If multiple intelligent species have evolved in Andromeda's habitable zone, they may have already confronted questions that humanity is only beginning to ask. How do civilizations detect one another across interstellar distances? Is interstellar travel possible? Can species fundamentally different in biology and cognition find common ground for communication? When astronomers search for evidence of life beyond Earth, they focus on two distinct categories of indicators: biosignatures, which suggest the presence of biological processes, and technosignatures, which point to technological civilization. In the Andromeda Galaxy, both categories present tantalizing possibilities for detection, despite the immense distances involved. Biosignatures represent the chemical fingerprints of life processes. On Earth, oxygen became abundant in our atmosphere only after photosynthetic life gained a planetary foothold. Similarly, methane combined with oxygen suggests biological activity, as these gases would normally react and disappear without continuous biological replenishment. While directly detecting atmospheric compositions of Andromedan exoplanets remains beyond our current capabilities, next-generation observatories may soon change this limitation. The James Webb Space Telescope has already demonstrated remarkable ability to analyze exoplanet atmospheres within our own galaxy. Its successor instruments, currently in development, may extend this capability to select planetary systems in Andromeda's nearest regions. These future observations will focus on detecting oxygen-methane disequilibrium, water vapor, and seasonal variations in atmospheric composition, all potential indicators of biological activity. More detectable than individual planetary atmospheres are broader planetary system characteristics. Chlorophyll and similar photosynthetic pigments create distinctive light absorption patterns across specific wavelengths. If plant-like organisms dominate large portions of an Andromedan planet, the reflected light spectrum might reveal their presence through these red edge signatures, sudden changes in reflectivity at particular wavelengths. Large-scale seasonal changes across planetary surfaces could potentially be detected through careful spectroscopic analysis of light from Andromedan star systems. Even more intriguing are potential technosignatures, indicators of technological civilization. These range from atmospheric pollutants to energy utilization patterns that defy natural explanation. While challenging to detect, technosignatures offer the advantage of being deliberately created for visibility or resulting from large-scale energy usage that stands out against natural backgrounds. Radio emissions represent the most searched-for technosignature. Advanced civilizations might generate radio signals for communication, radar, or other purposes that could be distinguished from natural phenomena through their coherence, modulation, or narrow frequency range. The Breakthrough Listen Project, humanity's most comprehensive search for extraterrestrial intelligence, has already conducted preliminary observations of Andromeda, focusing on regions within its galactic habitable zone. Optical technosignatures offer another detection avenue. Laser pulses, potentially used for communication between Andromedan civilizations, might appear as extremely brief, intense bursts of monochromatic light from specific points. The Panoramic Survey Telescope and Rapid Response System, PANSTARRS, and upcoming Vera C. Rubin Observatory could potentially detect such signals if directed toward Earth, whether intentionally or incidentally. Perhaps the most speculative but potentially detectable technosignatures involve massive energy utilization. Theoretical megastructures like Dyson spheres, hypothetical constructs surrounding stars to capture their energy output, would create distinctive infrared excess as they radiate waste heat. Advanced civilizations might engage in stellar engineering, altering their stars' apparent properties in ways distinguishable from natural stellar evolution. Recent observations from the Gaia spacecraft have identified several unusual stellar objects within Andromeda that exhibit unexpected light curves and spectral characteristics. While natural explanations remain most likely, these anomalies warrant further investigation. One star, designated Andromeda Anomalous Source 037, AAS 037, displays periodic dimming patterns that cannot be fully explained by orbital dynamics of natural objects, prompting intensified observational efforts. Waste heat signatures across mid-infrared wavelengths present another detection pathway. Any technological civilization utilizing substantial energy must ultimately radiate waste heat according to fundamental thermodynamic principles. Galaxy-wide analyses of Andromeda's infrared emissions, compared against models of natural stellar and dust distributions, might reveal regions with unexplained thermal excesses indicative of large-scale technological activity. The challenge remains distinguishing genuine biosignatures and technosignatures from natural phenomena. However, as our observational capabilities improve, our ability to identify truly anomalous features within Andromeda grows correspondingly stronger. The coming decade promises unprecedented insights into our neighboring galaxy's potential as a cradle for both life and technology. The temporal dimensions of evolution in Andromeda present perhaps the most compelling aspect of the case for intelligent life in our neighboring galaxy. To understand why, we must first appreciate the vast chronological canvas upon which Andromedan evolution might have unfolded. Andromeda formed approximately 10 billion years ago, roughly 2.5 billion years before our Milky Way achieved its current structure. This head start represents an evolutionary time frame almost unfathomable to human perception, more than half the current age of the entire universe. During this extended period, stellar formation, planetary development, and potentially biological evolution have proceeded without the major merger events that may have disrupted our own galaxy's evolutionary timeline. To contextualize this advantage, consider Earth's evolutionary history. From the emergence of the first single-celled organisms to technological civilization, required approximately 3.8 billion years. If life in Andromeda followed similar patterns but began just 1 billion years earlier than Earth, conservative estimate given the galaxy's age, technological civilizations might have already existed there while Earth was still cooling from its molten state. This temporal perspective transforms theoretical possibilities into statistical probabilities. Even if intelligent life emerges only once per galaxy, per billion years, an extremely conservative estimation based on the principle of mediocrity, Andromeda's age advantage suggests multiple technological civilizations could have already risen, perhaps even fallen, throughout its history. Technological advancement itself likely follows accelerating patterns similar to what we've observed on Earth. Our own species invented agriculture approximately 12,000 years ago, writing systems 5,000 years ago, and advanced computing less than 100 years ago. This accelerating pace of innovation, if mirrored by Andromedan civilizations, suggests they may have achieved technological capacities thousands or millions of years beyond our current capabilities. Such ancient technological civilizations might have already addressed questions humanity now confronts: sustainability challenges, artificial intelligence integration, interstellar travel limitations, and communication across vast cosmic distances. Their solutions would reflect not decades or centuries, but potentially millions of years of technological refinement. Paleoanthropologists note that on Earth, brain size and complexity increased dramatically during the last 2 million years of human evolution. An Andromedan species with similar cognitive development trajectories, but with a billion-year head start, might have achieved intellectual capacities fundamentally different from our own, perhaps developing forms of consciousness or cognitive architectures that human neuroscience cannot yet conceptualize. The concept of technological plateaus poses an intriguing question. Do civilizations eventually reach fundamental physical limits to their advancement? If so, multiple Andromedan civilizations might exist at similar technological levels despite evolving independently, having all reached the same natural ceiling imposed by physical laws. Alternatively, if no such plateaus exist, the technological gap between the most advanced Andromedan civilizations and humanity might be effectively insurmountable, a difference greater than between modern humans and single-celled organisms. Recent theoretical work in evolutionary astrobiology suggests that environmental pressures on different planets would likely produce intelligence through convergent evolution. Complex problem-solving abilities, tool use, and social coordination provide such powerful survival advantages that they tend to emerge repeatedly through different evolutionary pathways. On Earth alone, we see independent evolution of intelligence in corvids, cephalopods, cetaceans, and primates. Across Andromeda's billions of habitable planets, intelligence may represent not an evolutionary accident, but an inevitable outcome. Assumptions about technological advancement patterns must account for civilization longevity. If technologically, advanced societies typically survive only briefly before self-destruction or voluntary simplification, addressing what astronomers call the Fermi Paradox's great filter, then even Andromeda's age advantage might not translate to currently detectable civilizations. However, if even a small percentage achieve long-term sustainability, these survivors would likely have expanded throughout significant portions of the galaxy. The astronomical record itself provides indirect evidence supporting the possibility of ancient Andromedan civilizations. Unlike some galaxies showing signs of major disruptions, Andromeda's structure suggests stable conditions conducive to uninterrupted technological development over timescales far exceeding Earth's entire evolutionary history. Our neighboring galaxy Andromeda presents a fundamental paradox. If intelligent life exists there, why haven't we detected their communications? This question, a variant of the famous Fermi Paradox, applied specifically to our nearest galactic neighbor, frames what scientists call the communication conundrum. The distances involved create the first major challenge. At 2.5 million light-years, any signal we detect from Andromeda today actually left that galaxy when our human ancestors were still developing primitive stone tools during the early Paleolithic period. Conversely, any civilization in Andromeda observing Earth today sees not our technological society, but a pre-human planet dominated by early primates. This immense light travel time creates a communication delay that fundamentally alters how we must think about interstellar contact. Radio astronomy offers our primary window into potential Andromedan communications. Since the 1960s, radio telescopes have occasionally targeted Andromeda, though never with sustained, comprehensive coverage. The Breakthrough Listen initiative recently dedicated significant observation time to Andromeda, focusing on its galactic habitable zone with the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia. These observations can detect radio emissions equivalent to Earth's strongest transmitters from specific regions within Andromeda. However, several factors complicate radio detection efforts. First, any deliberate transmissions from Andromeda would need to be specifically directed toward our galaxy to be detectable. An unlikely scenario, unless Andromedan astronomers recognized the Milky Way as harboring potential intelligence 2.5 million years ago. Omnidirectional broadcasts, similar to Earth's early television and radio transmissions, would be far too weak for our current instruments to detect across intergalactic distances. Second, advanced civilizations might utilize communication technologies fundamentally different from radio waves. Directed energy systems like neutrino communications, gravitational wave modulation, or quantum entanglement-based technologies, if physically possible, would leave no detectable electromagnetic signature for our current instruments. Such technologies, representing potential advancements thousands or millions of years beyond our capabilities, would appear effectively invisible to contemporary human astronomy. Third, the communication methods of truly advanced civilizations might be optimized for efficiency in ways that make them indistinguishable from natural phenomena. Highly compressed data streams might appear as random noise, while precisely targeted narrowband transmissions might go completely undetected unless our receivers happen to be in exactly the right location, tuned to exactly the right frequency, at exactly the right moment. The concept of lighthouse signals, powerful sweeping beacons specifically designed to announce a civilization's presence, offers one potential solution. Such signals would prioritize detectability over communication efficiency, potentially enabling first contact across intergalactic distances. Several SETI researchers have proposed that technologically mature civilizations might maintain such beacons as cosmic welcome signs, rotating their transmission direction to periodically cover neighboring galaxies. Optical SETI presents another detection pathway. Advanced civilizations might use powerful laser pulses for either communication or as attention-getting signals. These would appear as extremely brief but intense flashes of monochromatic light. The automated Planet Finder telescope at Lick Observatory regularly conducts optical SETI observations, though Andromeda's distance stretches even these sensitive instruments to their limits. Perhaps most intriguing is the possibility that communication attempts from Andromeda have already been detected but misclassified as natural phenomena. Fast radio bursts, FRBs, millisecond duration radio pulses, of unknown origin, were first discovered in 2007 and have puzzled astronomers ever since. While most scientists favor natural explanations like magnetar flares, some characteristics of FRBs align with theoretical predictions for artificial interstellar signals. They appear highly coherent, incredibly energetic, and often exhibit complex internal structures. Several FRBs have been localized to Andromeda's general vicinity, though not definitively within the galaxy itself. Recent advancements in machine learning algorithms designed specifically to identify artificial signals within astronomical data offer new hope for detection. These systems can recognize patterns that might indicate intelligence without requiring specific assumptions about the communication method, potentially overcoming our anthropocentric biases about how advanced civilizations would communicate. When discussing potential intelligence in Andromeda, we often default to a simplified narrative, the search for a civilization. However, given the galaxy's age, size, and diversity of potential habitats, a more compelling model emerges. Andromeda may host not one but many different intelligent species, possibly numbering in the thousands or even millions. This multi-species hypothesis fundamentally changes how we conceptualize potential contact and detection. Andromeda contains approximately 1 trillion stars, with billions potentially hosting habitable planets. Even with extremely conservative assumptions about the emergence of intelligence, say 1 technological civilization per billion suitable stars, Andromeda might still harbor hundreds or thousands of distinct intelligent species that evolved independently on different worlds. The timing of evolutionary emergence creates another dimension of diversity. Some species might have achieved technological capability billions of years ago, while others could be emerging into their technological phases contemporaneously with humanity. This chronological distribution creates a potential spectrum of technological advancement spanning millions of years of development. Biological diversity adds further complexity. While convergent evolution suggests certain traits, like bilateral symmetry, sensory organs, and manipulative appendages, might be common across species, the specific evolutionary pathways would likely produce profound differences. Intelligence itself might manifest through neural architectures fundamentally different from mammalian brains, perhaps utilizing different biochemical substrates or organizational principles. This diversity would likely extend to cognitive frameworks. Different species would perceive reality through unique sensory systems, process information through distinct cognitive architectures, and develop technologies reflecting their particular biological capabilities and environmental challenges. The resulting civilizations would likely diverge dramatically in their technological trajectories, cultural structures, and communication methods. Several potential scenarios emerge from this multi-species model. First, Andromedan species might have developed interstellar communication networks spanning portions of the galaxy. Such networks would likely employ communication technologies optimized for their specific biological and technological capacities, potentially unrecognizable to human observers unless deliberately designed for cross-species detection. Second, older civilizations might have developed observation or contact protocols for emerging technological species. These protocols could involve long-term monitoring without direct contact, a cosmic version of anthropological non-interference principles. This would explain an apparent silence despite abundant intelligence. Third, more advanced civilizations might have transcended their original biological limitations through technological means, creating post-human or post-biological entities with capabilities and motivations fundamentally different from biological intelligence. Such entities might focus on projects incomprehensible to emerging civilizations like humanity, operating on timescales and in domains that render them effectively invisible to our observations. Recent theoretical work by astrobiologists suggests that if multiple technological species evolve within a single galaxy, they likely discover each other before developing interstellar travel capabilities. This contact potentially creates galactic clubs or federations long before physical interspecies meetings become possible. If such structures exist in Andromeda, they might include protocols regarding contact with neighboring galaxies like our own. The diversity hypothesis gains further support from Earth's own evolutionary history. On our single planet, intelligence has independently evolved multiple times, in primates, cetaceans, corvids, cephalopods, and potentially other lineages. Each represents a different neurological approach to solving complex environmental challenges. Extrapolated to a galaxy with billions of habitable worlds, this pattern suggests intelligence would take countless forms across Andromeda. This diversity creates significant implications for detection. Different species would likely develop technologies reflecting their specific biology, environment, and historical contingencies. The technosignatures produced would similarly vary, some potentially recognizable to human astronomy, others completely alien to our detection frameworks. Perhaps most intriguingly, the multi-species hypothesis suggests Andromeda might contain civilizations at technological levels similar to humanity's current development. Such civilizations might be engaged in their own search for extraterrestrial intelligence, perhaps even directing attention toward our Milky Way galaxy. The potential existence of intelligence in Andromeda extends far beyond astronomical curiosity. It strikes at the heart of humanity's deepest philosophical questions. If confirmed, Andromedan civilizations would transform our understanding of cosmic evolution, our place in the universe, and potentially the ultimate fate of technological species. First, confirmed intelligence in our neighboring galaxy would resolve the Fermi Paradox's most existential question: whether technological civilization represents a fleeting anomaly or a recurring cosmic phenomenon. Evidence from Andromeda would suggest technological intelligence emerges relatively frequently given suitable conditions, implying humanity exists within a universe where mind routinely develops from matter, a profound shift in our cosmic perspective. Second, detected civilizations in Andromeda would provide crucial data regarding technological longevity. The Great Filter hypothesis proposes that some developmental stage prevents most civilizations from achieving long-term sustainability. If Andromeda contains ancient civilizations spanning millions of years, this would suggest technological societies can indeed navigate existential challenges, offering hope for humanity's long-term prospects. Third, Andromedan intelligence would provide a unique opportunity to examine technological evolution divorced from human-specific historical and cultural contingencies. By comparing humanity's technological trajectory with those of independently evolved civilizations, we might distinguish which aspects of our development represent universal patterns versus peculiarities of Earth-specific circumstances. Looking toward future detection capabilities, several technological developments promise to revolutionize our search for Andromedan intelligence within the next 2 decades. The currently under-construction square-kilometer array, with sites in South Africa and Australia, will achieve sensitivity approximately 50 times greater than current radio telescopes when completed in 2028. This unprecedented sensitivity could detect radio emissions from Andromeda, equivalent to humanity's current electromagnetic output. Optical detection technologies are similarly advancing. The Vera C. Rubin Observatory, scheduled to begin full operations in 2026, will conduct the most comprehensive optical sky survey in human history. Its ability to detect brief optical transients makes it particularly well suited to identifying potential laser communications from Andromeda. Quantum astronomy, an emerging field combining quantum optics with astronomical observation, offers potentially revolutionary detection capabilities. Theoretical work suggests quantum-enhanced telescopes might eventually detect quantum communications between advanced civilizations, opening an entirely new observational window currently beyond conventional astronomy. Perhaps most promising are advances in artificial intelligence specifically designed for SETI applications. Machine learning algorithms can identify subtle patterns in astronomical data that might indicate artificial origin without requiring human programmers to specify exactly what signals might look like. These systems can analyze vastly more data than human researchers, potentially identifying technosignatures that would otherwise remain hidden in the overwhelming volume of astronomical information. Direct imaging of Andromedan exoplanets remains. Beyond near-term capabilities, but proposed space telescopes like the Habitable Worlds Observatory could potentially detect biosignatures from the closest regions of Andromeda within the next 30 years. Such observations would focus on spectroscopic analysis of atmospheric chemistry, seasonal changes in surface reflectivity, and potential indicators of large-scale environmental engineering. Gravitational wave astronomy offers another promising frontier. Advanced civilizations might generate distinctive gravitational wave patterns through massive engineering projects or exotic technologies. The planned Laser Interferometer Space Antenna, LISA, scheduled for launch in 2037, will provide sensitivity to gravitational waves across frequencies potentially useful for detecting such activities. As these detection capabilities advance, humanity faces profound questions about potential contact scenarios. If we detect evidence of Andromedan intelligence, what response would be appropriate? Should we attempt active communication despite the 2.5 million year response delay? What protocols should govern humanity's transmission of information to potentially advanced civilizations? The search for intelligence in Andromeda ultimately represents more than scientific curiosity. It forms part of humanity's broader quest to understand consciousness, technology, and our cosmic context. Whether our investigations reveal a galaxy teeming with diverse civilizations or an empty spiral of stars, the answer will profoundly shape our understanding of intelligence as either a cosmic abundance or precious rarity in an otherwise mindless universe. In either case, the quest itself reflects something profound about human nature. Our persistent drive to reach beyond current limitations, to seek connection even across intergalactic distances, and to understand our place within the vast cosmic story that began nearly 14 billion years ago with the birth of the universe itself.